So we were working essentially with entropy formulas. Okay, so let me make a definition, which I already did, but let me do it again. So let f from m to n, this, we'll put C1 plus Helder because we all care about C1 plus Helder. Just to make the definition, is less is enough, but actually C0 should be enough for the definition, but anywhere. And diffeo. Now we let W be a foliation. So, and here by foliation, what we really mean is a partition of M. Maybe let me be more specific. Let's not call it foliation. Let W be a partition of M into sets, into Borel sets. Actually, the fact that they are Borel sets will be a consequence of the following, such that there exists xi a measurable partition of M such that 1 if xi is larger, so let me just do it with sets, it's simpler for me. So it's this increasing property. Second, let me just do it easily this way. Diameter of f minus n of psi of x go to 0 for every x. Three. So this is telling us that this is essentially the xi is inside the unstables.
So do you measure that diameter using the global distance or the
the global distance.
Okay.
So the ambient manifold.
So it's kind of like Quayle.
Yeah, actually there is an almost equivalent definition. Probably it's even better the equivalent definition. Let me write down, which is the intersection of these guys is just the point. Actually, this is even more interesting than the fact that the diameter goes to 0. It's slightly different. Notice that I'm not putting a measure here yet. If I put a measure, then there will be some relation between convergence in measure versus almost everywhere convergence. But this is what it is. So this is an decreasing intersection because of the property above. And I'm just asking this to be the point. 3 is how the xi relates with the w, and the relation is when you go the other direction. So this is the union of fn of xi so that's how the w relates with the previous. And there is a fourth condition, which I will make a little bit less nice, but essentially it's a consequence. So this, I will write it down even though it's a consequence of 3. Or should be a consequence of 3 after all, which is there are long flow boxes for W, so that I can apply the second Rokhlin lemma to this W as well. I think that's all I need essentially. Again, 4 is essentially a consequence of 3 plus the fact that Xi is measurable. So there are flow boxes for Xi. That's the measurability. That's almost the definition of measurability or equivalently. And then by iterating these flow boxes for Xi, you have the long flow boxes for W essentially. So, okay. So these are the nice type of partitions we will be working all the time. And then for definition is if mu is an invariant, an F invariant, ergodic. I always like to ask ergodic even though if it is not needed. Here it's also not needed. But measure, then we define h mu f w as h mu f psi. Okay, and that one we already defined, so this is the same as minus integral logarithm of mu psi x of f minus 1 psi f of x d mu. Okay, so, and of course the first lemma is to claim that the definition is well defined, and the fact that it's well defined, so this object, it is well defined. And the reason why it is well defined is because under this setting, mu, and that's even a consequence of the proof of the second Rokhlin lemma, is that the mu psi x is nothing but the mu wx over mu wx of psi of x. So you normalize this to be a probability, and this measure is nothing but that, and this only depends on the psi on this normalization and nothing else. So if I take 2 different partitions, the corresponding psi measures will essentially coincide, which means that these integrals here will coincide after just making a simple computation. Okay. So yeah, actually, a simple computation will tell you that if psi1 is, if you have this, of course you need to ask a little bit more, but that's, let me put this way, and mu psi2 of psi1 of x is positive almost everywhere, so mu almost everywhere. So if the atoms has positive psi to measure, then the entropy for psi1, so since these are a little bit smaller, or quite a bit smaller, this tends to give you more information than the previous. So if I remember correctly, that's what you are supposed to have, and that's just Jensen inequality. Okay, so this is the proof of this Jensen inequality. So that's lemma 1, and lemma 2 will say that h mu f psi is equals to h mu of f psi. So you have these two properties, and once you have these two properties, then you take any two partitions, psi1 and psi2, as in the game, and you consider fn of psi1. So you iterate this, which is this partition. So you make the atoms to get increased, and then you use property 3 and property 2 and all the properties you have over there to make sure that the measure of the set of points where this is true goes to 1 as n goes to infinity. And then once you have this, you go to this statement here, not quite to this statement, but to the proof of this statement, and you get this property here. Okay? And then you go again to this statement and see that the entropy for this guy is essentially the same as the entropy for the psi1, which is then smaller than the entropy for the psi2. And then that way you prove that the entropy for the psi1 is smaller than the entropy for the psi2. And then you reverse the roles of psi1 and psi2 and you are done. Yeah, this is a completely abstract measure theoretic segment, so you don't even need the zero, you just need a transformation of a measure space, of a Borel measure space. Yeah, actually, you are right, so let's Borel measure. Let's say invertible because I am playing a little bit of invertibility here. But again, what I have in mind is this unstable solution, but it is useful that it's this general situation. Okay, so this is completely abstract measure theory. Now, let me move to the smooth ergodic theory, Pesin theory, and go back to coarse directions. So this is a theorem, which actually is a corollary of Pesin's stable manifold theorem. Actually, it's a corollary of all Pesin theory, but anyway. So, again, we have alpha, ck, let's do ck, rk is the same. And actually, when it comes to serious application, most of the time you go to the rk doing the suspension construction because it's really much simpler to deal with stuff. And now we have this, which you, as we said, we just need this. This business of belonging to LK, I think it's LKK was, or LK1, or LK1, because LKK is LK. Anyway, so, or if you want M is compact, and then we are happy. And probably, maybe that's good enough. Maybe we need epsilon more about the Helder norm. I don't think so. But anyway. Okay, we have this alpha guy, and let Txn be E1 plus EL. And actually, let me the splitting into coarse Lyapunov directions. So it means that each of these guys is by itself a sum of E sub S or E sub R in some index families of Fi's, and you have that the limit as n goes to infinity of logarithm norm of dxf, dx alpha n of b minus psi I of n divided by n goes to 0, and psi I is, or psi, maybe I should say psi r. This is when b belongs to this ER, and I know that psi r is positively proportional to any of the elements there. So psi t or rt in Fi. So any two such guys. So that's, and this is maximal with this property. So that's these are the coarse guys. Or there is the equivalent definition, which is even more important. Equivalently, E I of x is equal to the intersection of EU and psi. Of n is positive, where psi I of n is any of these members of the Fi. So this positivity doesn't make any change if they are positively proportional. Anyway, so these are the possible definitions. But what is important here is that for every j, no, EU actually, that's also true. So this intersection is correct, but it's also true that EUN of x, because here is intersection over all n's such that psi I of n is positive. But EU of x is also the sum of EI of x, which again now is in the i's. Yeah, maybe let me. Let's use another blackboard and let's do it because this is important. So EI of x is the intersection over all the n's such that psi I of n is positive of EUN, but it's also true that EUN of x is the sum over all the i's such that psi I of n is positive of EI. So you have these two ways.
Okay, so the second row defines EUN.
Exactly. So this defines, actually, well, you can further define EU by just the fact that the vectors that goes to 0 in the past. Okay? And yeah. For iterates of alpha n. Now, Okay. Okay, so this is so far the setting. Actually, my bad. Okay, in all this setting, mu is alpha invariant, ergodic. And as I said, I asked ergodic before there, and I didn't really need it. The same way I don't really need it here, ergodic, if I'm allowing really everything to depend on x. But if I ask ergodic for the whole system, for the whole action alpha, then all these quantities will be constant in x. Well, the xi, not the ei's. But I don't need the individual elements to be ergodic. That's especially useful over there where I will not have a priori that individual element will be ergodic, and I still want to talk about entropy. So I don't actually need ergodic here. Anyway, so what the Pesin Stable Manifold Theorem is telling us is that there exists for mu almost every x, there exists manifold, a CR manifold tangent to EIX at x, such that actually I have the same description for this Wi of x, and you could use it as a definition, but the fact that it's a manifold, you have to work a little bit. It's not too hard, it's just a transversality issue. So this is intersection over all n's such that psi I n is positive for the unstable manifold for n of x. Okay, so this is given by Pesin. These are CR manifolds. You intersect them and some transversality, and this intersection property will tell you that this is actually a manifold.
And is R equal to 1 plus alpha?
Yes. Absolutely. And actually it's more differentiable, so maybe let's go over there because it's better to keep track of differentiability for future purposes. So R strictly larger than 1. And then this is as differentiable as the diffeo. And this partition into Wix manifolds satisfies the conditions to define entropy h mu alpha of n w I whenever psi I of n is positive. If the psi I of n is 0 or negative, then this will not be increasing. So we will not have this property or this property, and then it will not be possible. And the proof, as I said, is Pesin Stable Manifold Theorem, some transversality, and for this you pick your n, fix n such that this property is true, then pick the unstable for the n, the WL will be inside this unstable for the n, by definition of the WI, and you pick your Sinai partition, xi u, and then the xi, so proof, you take the xi as being the sin I, and you intersect this with the Wi. And that will do the work. So that will satisfy this property automatically, this property automatically, this property also automatically, by all the properties of sin I partition. And then you have a well-defined entropy number.
So in the case of flows, let's say that alpha is defined on Rk.
Yeah.
If that map is Cs, do you have any difference with the regulation of Wi, or does it not?
No, it's the same. So if the flows is CR, then you have CR. There may be, so there may be some discussion there, but that's will fall in a different subject essentially. Whether you are CR, so each individual diffeomorphism is CR, but the dependence on the time is less or more regular. So there is this sort of discussion, but in a sense, at least in this setting, I think it's correct what I'm going to say, is that if for every time t, your flow is CR, then essentially the flow is CR as dependence of t as well. Or you can pretend it is CR as a dependence of t by making some conjugancy, some change of parameters, or some according modification of the time up to a cocycle in a sense. So then there is no disagreement between smoothness of the time and the diffeos transversely in a sense. But yeah, so if it were an RK action, all definitions are exactly the same. Simply put n as being in RK, and the rest remains without any difference. Okay, so we have these quantities. And the main lemma here actually is a theorem, which is actually a consequence of Huyi Hu. Of a relative version of Huyi Hu, but it's pretty much the same proof as original Huyi Hu, because remember that how I build the partitions, it's just sin I partition times that, so it's really, I don't need to do anything very, very specific. So, corollary of Huyi Hu is n into h, okay, n belonging to this subspace into h mu alpha n wi is linear. Okay, and the reason is the same proof as with Huyi Hu. So if I take n and m, choose sin I partition working simultaneously for alpha n and alpha m, and use definition, n is an inequality, and the basic formula we were discussing to obtain that h mu alpha n plus m is equal to obtain this. Oops, wi. Actually, a little bit more will be true, which will be very useful later in what I want to do next, is I could restrict my attention to some vibration I have and just restrict to the Wi inside this vibration, but I will be more explicit in there. Yet I will be able to define this sort of fibered coarse directions. I will still have this in I partition wedge, this fibered, and we will have this linearity here as well, and everything as before. So this is a linear guy now, which means so it's a linear guy, which you can, even it's only defined on a half plane, not on the other half plane, but you can check easily now that is positively proportional to this psi I. So a corollary of the corollary is that there exists some constant Ci larger than or equal to 0, because it could be 0. That's certainly one possibility, such that h mu alpha n is equal to Ci I of n. And again, of course, this Ci depends on what's your choice of coarse Lyapunov exponent. I told you what was my favorite choice, which is taking the Jacobian along the Ci, but take any other choice, you will just change what is the value Ci. But it's important that this number does not depend on the Ci, on the n. So it depends on the I, but not on the n. What are these numbers? Who knows? So they are whatever they have to be. If you make the choice, as I said, of this guy being the Jacobian, then you can show that this number is between 0 and 1. So it could be 0, it could be 1, or any number in between a priori. So let me go to one example, the most trivial example, but it's a very important example. Take k equals to 1. So alpha of n is just f to the n for some diffeo. Okay? Then in this case, you can check that EIX is either EU or ES, depending on whether you are considering positive or negative. So, because here the exponents psi I goes from Z into R, and then the kernel, assuming they are not 0, the kernel is just 0, and you have only two classes. Both are positive or both are negative. So, and these two classes is just one for the unstable and the other for the S. As I said, you may have the EC, but let's forget about the EC for that theory here. And so in this case, I'm just saying h mu of f WU, which is, on the other hand, h mu of Fn. This is n h mu f actually. So this we know, and this is the same as what I wrote upstairs. This is the same as Ci psi I of n, and this being a functional is n times something. Okay, and yeah, it's not much information, because the only relevant information of this writing here is the linearity. Well, it's also proportional to the xi, but in this one-dimensional situation, since you are allowing the function Ci, is very weak statement. Okay, so that's, as I said, it's a trivial, but it's an important example that you are generalizing what is happening for one diffeo. So you want to know what happened in this just one diffeo situation.
I guess you want to put absolute value of n.
Yeah, or assuming I'm in such a way that I'm talking about xiu positive, but yeah, if I point both guys together, then you do what Alf said. Then here you have, and you have to make your right choice of plus or minus according to what happens with the n. Yes. So
So is it true that if, in the general case of law, if your entropy is globally linear, then it has to be zero?
no.
Just like here.
No, it's not globally, so it's only linear in half planes.
I know. I'm saying if it's globally linear,
It has to be zero because it can never be negative. Entropy can never be negative, so there is no way you have linear without negative values. But there is a related notion, which is some sort of convexity, which I plan to discuss in a second. Yes. So, but I wanted to say one more thing before, but for that I will need to remember what I wanted to say. Okay, let's move on, and when I remember what I wanted to say, I will say. It was in this direction, so of what type of linearity. So after you have this theorem here, this corollary actually of Huyi Hu, you get this theorem which is actually a corollary of whatever we have discussed using quite a bit of linear algebra and not getting very badly mixed with the combinatorics of this linear algebra. Which says the following. So let alpha be as before. Mu ergodic, alpha invariant, then h mu alpha n is equal to the sum over all the i's such that psi I n is positive, coarse guide directions. Oops, no, yeah, all the i's. This is right. Of h mu alpha n wi. Okay, so the entropy is split into the sum of the contributions of all the quarks. So each quark has some contribution to the entropy, and then you add all these contributions and you get the total. And as I said, it's some sort of linear algebra. Remember that I said that this was linear by Huyi Hu on the corresponding Veil chamber. This quantity is also linear on the very same Veil chamber because the Veil chamber is characterized by these properties, all the n's which has the same set of i's. And you have two linear maps from Rk to R, and you want them to match. So that's just a matter of vectors. Okay? So you have to make them match in a basis for Rk. And you have linearities of these individual guys plus that. Then you play a little bit of of Lattice-Young formulas, and you get it. So yeah, once you know this is linear, then you just need to, so you can even go and restrict fully to a very small cone where in these cones all the Lyapunov exponents keep the same inequalities, so don't change inequalities. Then you apply Lattice-Young to this, and you have full linearity here. Then you have to discuss of how this Lattice-Young agrees with that formula here and these formulas here. It is subtle because you don't want to have in between, for instance, you have 2 times psi1 and psi1, that corresponds to this first one, but then you have psi2, and if psi2 is smaller than these two guys, you will be fine in the Lattice-Young. If the psi2 is larger than this guy, then you still will be fine in the Lattice-Young. But if this psi2 lands in the middle, then it's a pain. Then it was not the right choice of these guys after all. You should have made a better choice of these cones. Actually, the best thing to argue, and that's why I say it's really painful, the combinatorial aspect. So you start from the boundary, which is the kernel of one of the xi's on this Weyl chamber. And then, since you are in the kernel, you make sure that this xi naught is close to 0, so it's a smaller one. And then you show some equalities between what you have here and what you have there. You remove this last guy and then move on. It's some combinatorial argument. It's very painful, I have to tell you. But it's not really very hard. It's painful if you are like me and my collaborators don't like much combinatorics. So yeah, that's I should say. So this is by Aaron Brown, Shiren Wang, and myself. Okay. Yeah, one thing I forgot, which is a related matter to this, but it's about Pesin's entropy formula, but that comes here. So theorem, which is Pesin's entropy formula. We say that if mu is absolutely continuous with respect to Lebesgue, then h mu f is the sum of all positive exponents of the xi I, or actually to be just to be careful with multiplicities, we do it this way. Okay, so that's the standard Pesin entropy formula, but I like better an equivalent statement in this setting, which is not that, which is this is the same as the sum over all i's and then of course I have to count multiplicities, so that's why it's not the same guy. So let me just counting multiplicities. And I prefer to write it this way, so because then you don't distinguish between positive and negative, you just add the absolute value of all the exponents, you have to divide by half. And it's certainly a corollary of this, so it's just the fact that the entropy for the future is the same as the entropy for the past. Then you put both formulas together and divide it by 1. So it's not really a very smart thing, but I think it's an important writing when it comes to actions and actually to your question, Alf. Because a corollary of all this is that n is a seminorm. okay, whose unit ball, and that's a very important, is a polyhedron. So it's not just any convex set. Well, when I say polyhedron and unit ball, I'm really focusing in the case of it is a norm. If it is a seminorm, you have a kernel, which is a subspace where you have fully zero, and then transversely to this subspace where you have fully zero, you have this polyhedral type, which is finitely many guys. And this is just a corollary of this formula, and the fact that these guys are linear, and the formula we have for this very specific guy. Because the formula is that following these absolute value games and blah, 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 is that this is roughly, if I do it correctly, well, it's something like this. Ci is something of this form. Okay, so one have to be careful with that, but that's pretty much what it is, over all possible i's. And that's the ultimate. So maybe the CIs are not the same CIs as before. It's different CIs chosen accordingly with the 1/2 and all this business. But that's how the entropy norm looks like. Okay. So there is a nice discussion on all these matters in our paper with, if you want to look at it, is with Anatol Katok, Svetlana Katok, and again myself. Okay, so I guess time is up. It's almost up, so I will not have much more to discuss. Although I want to continue to discuss a little bit more this formula next time. Let me just draw the picture of what I want to do. So imagine you have two systems, which is one a factor of the other. Alpha, rho, both are CK actions, and one fibers over the other. Okay, then you have the entropy function here, the entropy function here. Now, how are they related? Well, individual entropy numbers are related by Abramov-Rokhlin, which I will write down again here next Wednesday. Now, imagine you know a little bit more about this pi. Imagine it's a smooth submersion so that you have fibers, what you are collapsing is some compact fibers there. Then you really have a very nice picture because pi is smooth. So it means that the fibers are submanifolds, which will be an invariant guys. So which means that the Lyapunov exponents will decompose as Lyapunov exponents corresponding to the fiber, or Lyapunov exponents which has component perpendicular or transverse to the fiber, which are particularly Lyapunov exponents which come from the base. So then I have on one hand Abramov-Rokhlin formula, on the other hand I have this geometry. I have directions which are collapsed by pi. I don't know anything about them downstairs, and I have directions which are perpendicular to pi, so they are seen downstairs. Now, what happens with these entropy contributions from different Lyapunov directions above and below? And that's what we are going to analyze. And we'll try to discover some nice phenomena coming from there. Okay, so that's what we are going to do on Wednesday. Okay, that's it. Thanks. So last time we got a reasonably nice formula for the entropy. So let me remind you what it was. I have Ck, or the same will go if you have Rk acting on a manifold preserving a measure mu ergodic. This is alpha, CR function, alpha larger than 1. And we have the Wi where the coarse Lyapunov foliations. So these foliations is in the Pesin sense. And then we got the formula saying that H mu alpha n is the sum over all i's, or such that I of n is positive, of which you can forget about this if you define this quantity as being 0 whenever this direction is contracting or have 0 exponents. And that's a very important formula, which we plan to explore a little bit and play quite a bit with these quantities when you have factors. So let me see what I want to do now, because there are different versions of what I want to write. So yeah, let's move to the nicest version and to the strong theorem that is behind what I'm trying to do here. So let's go back to our gamma acting on a manifold. Maybe it's the m, but it's not the same m as there. Preserving a measure mu. Remember that I said here that m typically is compact, but actually whatever is happening here goes through even if m is not compact, assuming you have whatever integrability condition needs to be done. This is important because now I am assuming gamma is a lattice, which means that the quotient G mod gamma may not be compact. Of course, you can just think of co-compact lattices and then there is not a problem, and the space will be compact. But if it is not co-compact, still the theorem are true, just because of this. Now M is compact. Again, one can relax these assumptions, but let's not do it. So you have this action there. And no measure, sorry. So no invariant measure so far. Invariant measure will show up later. So this is alpha, and again is C1 plus Felder diffeos. Now I will start again what we have played in this Margulis normal subgroup theorem, and I want to find an invariant measure for this gamma action. Okay, so remember that that's what was this Margulis normal subgroup theorem about, finding an invariant measure for actions. So I want to understand how can I get this invariant measure, and what is stopping me from finding this invariant measure. So we know that, say, in the setting we care G, S, L, and R, so we know that there are actions without invariant measures, so we don't hope to always build an invariant measure. So we really want to understand what's stopping us from there. So what we do? We do the suspension m alpha, which is as always g times m mod the action. Now we have this projection pi from m alpha onto g mod gamma. And now we take a measure, since we are not going to need more than that, take a measure mu such that 1. Mu is invariant under A, so equals to diagonal matrices, positive entries, so this Cartan subgroup, and 2, the projection of mu onto the G mod gamma is Lebesgue. So we know it projects to Lebesgue. Well, that's the only 2 things I really care about this measure. So now I have m alpha, I have G mod gamma, I have Lebesgue here, I have mu here. This is the projection. I have the diagonal group acting here, and the diagonal group preserves these measures. I have the whole group action G acting upstairs, downstairs. Downstairs, the whole group action preserves the lambda measure. Upstairs, it doesn't. It's only the D that preserves this measure. Okay, good. But as I said, I have the whole G group acting up here. And so I may ask myself individually for each individual element of the group, G acting up here, whether the measure is invariant by this guy or not invariant by this guy. And as we did before, we have this set G mu, which are all the G's in G's, such that G star mu equals to mu. And this is naturally a closed group. And I want to understand a little bit better about this group G. So very specifically, I want to do the following. I take any of these Hij guys, this S in the ij direction. So I take any group. It could be upper or lower triangular, I don't care. I'm not caring about diagonal because I already have invariance along the diagonal. And I want to check whether these guys, this group, belongs to this G mu or not. And I want to do it from a geometric perspective. Okay? So first thing to observe is that I have here on M alpha this foliation by Hij, which come from the action of the group G on M alpha. Okay, so this induces this foliation here, which project into the corresponding foliation down here. Now, if I take a vector tangent to this foliation, it's a vector which is inside the G orbit. Okay, and whatever is happening inside the G orbit, you don't need to think outside of the G orbit, so transversal to the G orbit. And here the game is the same as what we did in Margulis' normal subgroup. So if we are not looking perpendicular to the G orbit, we don't even care M is a manifold perpendicular to the g-orbit, because we are only looking tangentially. And along the g-orbit, the infinitesimal behavior will be the same downstairs than upstairs, because the projection restricted to g-orbits is a diffeo. Which means that when I apply the diagonal element to this hij, it's just multiplied by e to the ti minus tj. Okay, so what's the corollary of what I just said? Is apply Oseledets theorem to this action of Rn minus 1 into M alpha, and we have a coarse Lyapunov decomposition. Actually, we have a Lyapunov decomposition plus a coarse Lyapunov decomposition, which is also word equals to E1 plus E hat. Let's put the hat here because this is more important than that. And we know that this chi ij of t equals to ti minus tj are Lyapunov exponents. For this action. So there probably are more Lyapunov exponents, but I know I have these Lyapunov exponents. Okay? And actually, if I go a little bit finer onto this analysis, I see that Tm alpha naturally splits, first of all, at the tangent to the orbits plus the tangents to the m direction. Just the fact that the g times m splitting, so this product structure of g is preserved by my g action, not just for the dynamic, but for the whole g action. So this splitting being preserved, it means that the Oseledets splitting, this one, not the coarse, will be split into this Oseledets plus this Oseledets splitting. So then I can go a little bit more carefully and write down this part as, and this guy I fully know what is the Oseledets splitting because it's the one coming from the G mod gamma and actually just the G action. So this is the sum of Eij, upper and lower triangular, which coincide essentially with the coarse, plus the tangent to the diagonal guy. So these are the zero exponents, and these are the chi I j of t equals to ti minus tj. And you see, since I'm working with SLNR, that's exactly what you get, and there are no coarse, so no non-trivial coarse. So each of these guys is one-dimensional, the Aij. So there are no positively proportional elements. Okay? Now, what happened about Tm? Now, Tm is unknown because it depends on what is alpha. And no one told me anything about Tm. But Tm will have a splitting with Lyapunov exponents chi r. And actually, I care more about the coarse guys, where f here stands for fiber. Okay, so it's just to emphasize that these exponents are the guys coming from the fiber of this fibration onto the G moduli. These are coarse guys. Now, fiber coarse, actually. There may be some guys up here which are proportional to these guys. Okay? So we have the exponents, the coarse guys, psi if or psi kf, and some of these guys may be proportional, even equal to some of the guys there. So that I don't know. Maybe there is just one big zero business here. Maybe they are all different from these guys, maybe not. No clue. But that's the structure I'm having.
So those are the coarse subspaces for the alpha action on M.
This is a subtle game. So you define, so one way of this, there are two ways of defining it. One way is just do Oseledets theorem not for derivative cocycle, but just for any cocycle. And if you do it for any cocycle, you look to the cocycle coming from the D action. So is the derivative restricted to this Tm guy? So d alpha t restricted to Tm. And now this is a matrix cocycle if you do the right trivialization. And you apply Oseledets to this matrix cocycle. And then it will give you this decomposition. That's one way of arguing. The second way is you apply Oseledets to the derivative cocycle, as we did before and explained before. And then you take your coarses, defined everywhere, and you intersect it with the tangent to the M direction. This intersection could be trivial. Okay? But whenever non-trivial, it will correspond to one of these guys. That's the second definition. There are some statements to check in this way or that way, and actually it is useful to have a statement that tells you that both ways give you the same result. And these two statements come from the basic properties of Oseledets plus uniqueness, which is similar to what you get from Jordan, which is that if a matrix is done in blocks form, and that's the whole point of preserving this splitting, is that the derivative clock cycle is given in blocks form, then the Oseledets splitting is also in block form. Okay? So that's what it is. It's some linear algebra, essentially. But it's important because now we want even to go and look at the geometric version of what this is telling us. So, accordingly, given any coarse direction, E, it splits as E fiber plus E orbit direction. Okay, it's this block form of the derivative, where this may be trivial, this may be trivial, both may be non-trivial. If both are trivial, then I'm not calling it coarse because it's too trivial to care. Okay? But it may be just one of them being trivial or both non-trivial. And then accordingly, I have these coarse Lyapunov manifolds coming from Pesin theory, which will respect some structure, which is they will have a vertical foliation and an horizontal foliation. And this just comes from the fact that I have the G group action. And the G group, well, again, assuming these two guys are non-trivial. If one of them is trivial, then there is no much to discuss. But if both of them are non-trivial, so if both the EF and EG are non-zero, then I have these two guys. So these are the W, G, E, which is just the orbits by the corresponding group. So this guy, as we already make the analysis there, will have to be one of these EIJ directions, which has associated the one parameter group Hij, and these are just the orbits of this one parameter group Hij. Now the vertical guys just correspond to the fibers. So it's just the fiber through this point, which the fiber through this point is this guy, times intersected with this W Hx. And the G direction is just this Hij S G X such that S is in R. Okay? That's what it is. So it has this M. So this is inside the fiber. So it's the M part of the guys. This is inside the the group side. Okay? Now, this is always one-dimensional. I'm assuming not talking about the zero exponent direction. The zero exponent, I will never touch it. So the zero exponent corresponds to n-1 dimensions. But if you are not in the zero exponent course, this guy will be one-dimensional. In this case, in other simple Lie groups, you may have different stuff. But let's concentrate on SLNR. This is one-dimensional. This other guy could be zero-dimensional in case that this is not touching the fiber, so where the coarse part doesn't touch here at all for this Ij, or maybe 35-dimensional, full dimension M could be that. Okay, so this could comprise essentially the whole fiber, or an open set in the fiber. Okay. So that's the picture. Now, when you project this WE to the G mod gamma, this two-dimensional picture here goes into an interval. Okay? Now, let's try to understand for a second what should be the So did I put a notation here? Yeah, okay, let's call it mu. The measure is mu. Okay. So I have this course and I want to understand this number because understanding these contributions will imply understanding what is the entropy of the whole system. Now, to understand this, I need to understand what is the conditional measure along this WI direction. And I know that the measure mu project to Lebesgue. And I know that the condition of Lebesgue along the ij directions is Lebesgue. So this means that if I look at this WE guy, this mapping to the segment, I have this measure mu WE, and it will project into Lebesgue measure here. So ds into this ij j of s.
Can you write alpha of t? That's the g action.
That's the, yes, well, but I'm taking t in the diagonal. So it's the g action on m alpha, but I'm only taking t into the d, because if not, the measure is not invariant, so I cannot compute an entropy of someone that is not invariant. The measure is only invariant by under d. And remember, I asked two things to the measure. One is to be invariant under d. Well, A, sorry, A is the diagonal. And the second is that it projects to Lebesgue. So the fact that it projects to Lebesgue is what tells me that this conditional measure here will project into ds. And this is the naturality of Rokhlin theorem. So if things are correct. So it doesn't mean that the conditionals along the g orbit here, along the hij orbit, will be Lebesgue. So that's not the same at all. Okay, just telling you that this goes into here. And then it will have conditionals along the vertical FWEF, which are whatever they have to be. Okay, so we have not much of it. Now, if I apply Abramov-Rokhlin type of theorem, I would have that this entropy should be the same as the contribution of entropy coming from here, which is chi ij, because that's how you get the contribution here, plus the contribution from the fibers. So that's what Abramov-Rokhlin should tell me. H mu alpha t is equal to chi ij of t. So again, assuming t is positive, and here assuming coarse direction E contains this Eij direction, then this should be this base plus some fibered of WE subordinated with the fibers of the foliation, but this, by the very definition, is this, is WEF. Now, this is very well-defined object. We discussed it. This is just a very well-defined number, which happens to be h lambda for the e to the t1, e to the tn, applied to this w aij guy, which corresponds to this unipotent guy. So this equality is a straightforward computation, and you have this. But here is very important to note that I put should say. So I'm not saying that's what Abramov-Rokhlin say. Okay? Because Abramov-Rokhlin is about total system, total entropy. Okay? Entropy associated with finite partitions. It's not about all these conditional entropies we are discussing here. But we wish Abramov-Rokhlin say that. We really wish it. Actually, that's a theorem that says Abramov-Rokhlin is telling us that. So, under the previous construction, or assumption more than construction, we take ij, I different from j, let E be coarse Lyapunov direction positively proportional to chi I j equals to ti minus tj. So this very precise coarse Lyapunov direction, and then for every t such that ti is larger than tj, so chi ij of t positive, the entropy for alpha t of this measure mu, which, as I said, the main hypothesis is invariant on the diagonal, project into this guy. This is equal to plus the conditional entropy along this W, oops, this is not a mu, this is WE, sorry, WE fiber. So this may not be always true, but under the assumptions I wrote, this is true.
So what does it mean to say that the coarse Lyapunov direction is positively proportional?
Well, it's just so a coarse Lyapunov direction has associated a Lyapunov exponents. Actually, is associated to a family of Lyapunov exponents, all of them being positively proportional. And I'm saying all of them have to be positively proportional to this guy. So remember that the coarse Lyapunov direction is to group all the directions which has positively proportional Lyapunov exponent.
Right.
That's a coarse direction.
I see.
So then I'm saying, I take this ij, I take this Lyapunov exponent that I know it is a Lyapunov exponent, and I take the coarse Lyapunov exponent, or the coarse Lyapunov direction associated to this guy. So I may be adding other guys. And actually, the guys I'm adding will come only from the fiber, because from the G mod gamma, there is no one, from the G orbit, there is no one else coming. They only will come from the fiber direction. Maybe no one is in the fiber direction. And that's actually the corollary I want to state.
So that means that the G part of E may be bigger than Eij.
No, actually, that's, so in this SLNR, the G part of E cannot be bigger, because Ti minus Tj cannot be proportional to any other guy.
I see.
Because they are all of the form Ti minus Tj, and Ti minus Tj cannot be proportional to Tk minus Tl. But that is because it's SLNR. In other group, like in the symplectic group, I think, or in SOPQ, or in SUPQ, or whatever, these other simple groups, you have positive proportionality coming from the G direction. So these things happen. And then you have to be more delicate here in this discussion. Okay? Which is pretty much the same result, but again, you need to write correctly whatever it has to be. That's why I'm just doing SLNR, where it is just this one dimension along the G orbit, and nothing else is coming from the G orbit. So that's why here you have just this number. Because when you project, you just have this one dimension. So the G part of this coarse is just this ij direction, no one else. So I will apply this statement to a very particular case. So let me put a couple of definitions. So we call fiber Lyapunov exponents to all exponents coming from the fiber. Okay, and the ones coming from the G direction, they are called roots, because the chi ij's are called roots. Okay, so that's Lie group theory notation, representation theory notation. So the Lyapunov exponents coming from, so the non-zero, actually they could be zero. So the Lyapunov exponent coming from the G direction are called roots. So the roots of the group is just this Lyapunov exponent. And actually, if I were in some sort of linear situation, these fibered exponents are what are called the weights of the representation. But that I will probably discuss later, not now. So that's definition one. Definition two, the root chi ij is called resonant if there exists a fibered exponent such that that is positively proportional to the root. Otherwise, is non-resonant. Okay? So, coming to this picture, resonant root will mean that this space is non-trivial, or this manifold is non-trivial. Non-resonant root means this manifold is trivial. Okay? So that's what is resonant root or non-resonant root. You can also define resonant Lyapunov exponent and non-resonant Lyapunov exponents. It's not much use for us here, that's why I'm not defining it, but you can define it. Okay, so the corollary says that if chi ij is a non-resonant root, so always under the same assumptions because it's a corollary, then mu is aij is invariant for every s, i.e. Hij belongs to G mu for every s. So if it is non-resonant, so if I don't have any exponent in the fiber which is positively proportional to the psi ij, then the measure is invariant along this direction. And the proof is this formula, understood correctly. So under this assumption, I have that the WE is just the Hij orbit. It projects under pi into the Ij orbit. And the formula tells me that H mu alpha t of this WE, which is nothing but the Hij orbit, is chi I j of t, because this being trivial means this quantity is 0. So there is no quantity here. So this gives you a 0, so you get equality here. And then from here, the Drapier-Yang implies that this mu WE is absolutely continuous with respect to ds, which is the Lebesgue measure on this guy. And if you remember the formula we gave, it actually tells you that it's equal to ds up to a constant, so now it is ds. And this is exactly the definition of being invariant by this group. So I have this group acting. These are the orbits of this group. If the conditional measure along the orbits are hard measure along the orbit, then the measure is invariant.
And the proportionality constant will be exactly equal to the Ti minus Tj.
No, the proportionality constant actually it depends on some normalizations you choose. That's all. So it is true that, and that's important, and that's actually a way of reading this formula when you have this top guy, which is when I do alpha t star mu WE, this is e to the Ti minus Tj mu WE. So this on the point x, this on the point alpha t of x. Okay, so it's the proportionality constant when I apply the dynamics is e to the Ti minus Tj. And that's because I know that this guy is ds, and I know how it corresponds to ds. It's not a general fact. Okay, so what is this proportionality constant is sort of a mystery. It's a cocycle, and this cocycle has integral the log of this multiplicative cocycle is an additive cocycle, and this additive cocycle has as integral the Lyapunov exponent with some weights or something. So that's also more or less true. But again, that's more or less true because we don't have, in general, a good normalization for these measures. So these measures are only defined up to a normalization, which you cannot prescribe easily. If you prescribe, then you do have the cocycle. And then, yeah, what I said is essentially true. But, yeah.
Sorry, could you repeat how you deduce that mu's Hij invariance?
Because here is a complete general lemma. Yeah, maybe let's go up here. Yeah, let's go here. consider a flow phi t. So it's from n into n a flow. Okay, with whatever basic assumption so that you have long tubular neighborhoods. So take me a measure. Then mu is phi t invariant for every t if and only if the conditional measure along the orbits of phi x is proportional to dt for every x, for almost every x. So being invariant by a flow is the same as having conditional measure R. And actually this is not just for R, okay, so this is also true for G in G, then or this is R measure on G. Okay, and for this you only need, so this is a lemma which requires some hypothesis of reasonable amount of freeness for this action so that you have long tubular neighborhoods. And once you have these long tubular neighborhoods, then I can make sense of this. And once I can make sense of this, I can compare this with R measure along the orbit. And I can ask myself whether these quantities, so these two measures coincide up to a constant or do not coincide up to a constant. If they do coincide up to a constant, then the measure mu is G invariant. If they don't coincide up to a constant, then they don't. Actually, if you know that instead of this, this is equivalent to dg, then you don't get invariance, but you get quasi-invariance. Okay, so this guy will be the same as phi g star mu is equivalent to mu. Okay, this here is phi g star mu is equal to mu. And actually here you will have a Radon-Nikodym derivative, and the Radon-Nikodym derivative is naturally, so when you do d phi g mu d mu, this is some function phi of gx, and the way it moves, so it is a cocycle, and the way it moves with the g direction is essentially this Radon-Nikodym derivative here. So that's maybe with some adjustments, so one have to do whatever identification. So this is a lemma. It's not 100% trivial to prove, especially because you have to go and do all the Rokhlin business. But after you did all the Rokhlin business, is just you follow the definition and follow the natural steps. But it's a very powerful statement. So it's a very important way of thinking of invariant measures. Okay? And this is the way we are thinking here of this invariant measure. And here, the flow we are looking to think this way is the Orocycle flow, the flow HIGS. So here, we are looking to this flow. And we have this flow acting on the M alpha. Its orbits are these guys. And we want to know what are the conditional measures here. And then we apply our formula. The formula tells that this is true. And then Ledrapillon tells you that whenever this is true, you have that the conditional measures are not only equivalent to ds, but also the Radon-Nikodym derivative is constant, which then implies that you are equal to ds up to a constant. And this is invariance by the flow. So So let me show you an example of this happening.
Is there always a non-resonant root?
No, there may be no non-resonant root. Let me give you then two examples. Okay, let me give first the example, which is the fully positive example, which are the two paradigmatic examples. So the first example is take gamma equals to SL3Z. Okay, you make it act on the torus T3 the obvious way, okay, linearly. Then you know it preserves Lebesgue measure, okay? So that's known, but let's not care about knowing that it preserves Lebesgue measure. We want to really play with the business here. Now we do the suspension. So we have this M alpha, we have the SL3R here, we have this G acting on M alpha. I can take the diagonal group A, and it preserves, let's say, any measure. I don't care really which is the measure here. There are two favorite measures to be preserved here. One is Lebesgue Lebesgue times Lebesgue. So Lebesgue in G mod gamma times Lebesgue on the torus T3, or you can take Lebesgue in G mod gamma times delta 0. This is also will be preserved. There are other measures, not that many actually. Well, by the diagonal is whatever. Let's not enter into that. But for our discussion, really wouldn't matter which is the measure you will have, because the Lyapunov exponents will be completely independent of your choice of measures. And that's because this is a fully linear map. So the cocycle is independent of x. So you can see that you have these guys coming from these directions. So we have these 6 Lyapunov exponent coming from here, psi ij from the G direction. We have this 0 exponent coming from here, which are not interesting for our business. And we have the fiber ones, which come from the T3, which are psi L of T is TL. Okay, which correspond essentially to the splitting of T3 as E1 plus E2 plus E3 into 3 real eigenvalues. I have to be a little bit careful. I will be a little bit careful in 2 seconds to do this full description here. There is an important fact happening here that I will try to push. But this is not much different to what we did when we playing with 2 matrices AB and the C-square action, and we do the suspension. Here is pretty much the same. So actually, these are the weights of the standard representation of SL3R into R3, just as matrices acting on R3. So these are the weights of this representation. That's why Lyapunov exponents are sometimes called weights. Okay, now you see that these guys are never proportional to these guys. because Ti minus Tj equals to some constant Z times TL for every T equals to implies, okay, it's impossible, so actually it doesn't imply, it's impossible. Okay, so there is no way you have such a thing. So it means that every measure, so you see what is the corollary now, every measure, doesn't matter which. And from there, here we can make even the full classification. So it means that every measure mu, that is invariant by D, by A, sorry, and projects to Lebesgue on G mod gamma is fully G invariant. Because it will be invariant by all the psi ij directions. So it will be invariant by all these guys. And now I said something which was wrong, but luckily I didn't write it. So I told you, you had this measure, and you have this measure, and I said there are other measures. But actually there are no other measures. These are all of them. And it's just this statement. This measure is G invariant. Now once this measure mu is G invariant, fully G invariant, you can check that actually mu will have to be some measure nu. So we have to be a product measure that comes from the full G invariance. And this new measure will have to be invariant by the gamma action. So nu on T3 and gamma star nu equals to nu for every gamma in SL3C. And now simply apply, so do Fourier. So I get that the Fourier transform of nu applied to an integer will be the same as nu at gamma transpose n for every gamma in SL3C. And then it's really a simple exercise, because this is any matrix you want. Okay? So since this is any matrix you want, you have to play a little bit, but essentially, if you have whatever decay at infinity of this nu, this will have to be Lebesgue measure. So the nu hat of n will be 0 unless n equals to 0. And if you don't have any decay, then it will have to become 1. And then you have nu hat of n will be 1, whatever you choose, which is delta at 0. And nothing else can happen. Just play a little bit with the matrices. So the fact that this is true with a gamma transpose here for every gamma tells you that it is also true for every gamma. And then you take n. N can be taken always into a constant a of n times the first element in the canonical basis for some gamma, where this constant is the common denominator for all the entries of n. So the how it's called is the common divisor for all the entries of n is this a of n, and you can, so if the common divisor is 1, you can take into the first element of the canonical basis. And if not, you have this one parameter coming from this common denominator. So that's the first reduction. Now the second reduction is sending the gammas to infinity. And you use that as a measure, and I'm missing something else. I don't remember. You can do it. It's just really a very trivial exercise on linear algebra after all, how to get from this Fourier invariance to really the measure is So these are the only two examples. So this proves that the only measure which is invariant by these guys are delta 0 and Lebesgue on the torus. So that's one application. The second application is the other paradigmatic situation. I guess I'm probably over time. Yes, as always I am. So let me write down what is it, and then we do the analysis on Friday. So we again take G equals to SL3R. Gamma now is really doesn't matter. It's any lattice. SL3Z will do. And now the manifold is S2 or RP2, depending on what you want to think. And actually, is G mod Q, where Q is this group. And you have the natural action of SL3R, and actually we just care about gamma on this S2 or this RP2 by projectivizing lines to lines or half lines to half lines. Or you do the action multiplying on this direction G mod Q, but it's geometrically this action. And then we can go and look at the invariant measures and Lyapunov exponents. So we are going to do it on Friday, okay? And see how is the other part.
So the second example is an example where
you will have resonant roots. And the non-invariant, non-full invariance of the measure will come exactly from the resonant roots. So there is no G invariant measure for this guy. There is no option for a G invariant measure for this guy. And the reason why there is no invariant measure has to come from some root explanation. Because the theorem says that you will gain invariant if there is no resonance. So there should be some resonance. There will be some fiber exponents which are resonant with the roots. But we are going to do the computations on Friday. Okay, thanks. See you. So let's go back to the examples and to this resonance versus non-resonance, because this is very important subject. So let's remember the example 1 is G is SLNR, SL3R. Let's just do the SLN because it's not really much of a difference. Gamma is SLNZ. Gamma acts on the torus Tn by linear maps. It's how the matrix acts on the torus. And we go do the suspension and blah blah blah. And the claim is that the fiber guys, which correspond to tangent to Tn, this is the sum of the i's of actually that's depend on the G. Let me do it this way. Over I for almost every pair Gx in G times Tn mod relation. But actually, this is almost lambda, almost every G in G mod gamma. Because as we will see, the splitting does not depend on X, only will depend on G. Okay, and this is because it's just some linear map, so there is no difference what happens between one point and the other. That's why we don't really care about this. And the Lyapunov exponent chi I, so the coarse Lyapunov exponent chi I of t for t e to the t1 e to the tn is actually, the coarse is just one dimensional, so it's the same as the exponent that is exponent ti. So the linear matrix, the diagonal matrix essentially acts as itself on this place. What do we care? There is one thing that we do care is that the measure mu invariant for the diagonal guys acting on this guy. There is also a diagonal guy acting here, and we care that the measure mu here project into lambda. So we do care about that. There are other measures invariant by the diagonal that do not project onto lambda. We will discuss it in a second, which are these other measures. But we care here about the measures that actually project onto lambda. We could ask a little bit less, so we can discuss it even there. Still, the theory more or less will behave very reasonable if you ask less than mu projecting into lambda, but at the end of the day, they will be projecting into lambda. So you will be part of the proof will imply so that if the theory is working, then mu eventually will be projecting into lambda. So it's not much of a problem. But in any event, so this is our standing situation. So we have also the psi ij exponents, which are ti minus tj, which correspond to the splitting of the tangent to the group as sum of these eij directions, which are the cycle guys, and then we have plus the tangent to A. And the diagonal, which are some zero exponents coming from the G group. Again, all these essentially come from the G action, which are projecting to the corresponding guys here. So you see that this guy, none of them can be proportional to this, because this is a functional, this is another functional, and these two functions are not proportional to one to each other. And so this implies that the measure mu, which was only invariant by the diagonal, now is invariant for everybody, for every hij direction. And once it is invariant for every hij direction, it is invariant by the group, and then it's fully invariant. And as I said, when it is fully invariant, it has to be either delta 0 or so delta 0 in the torus Tn times lambda, or Lebesgue on the torus Tn times lambda. Now let's do a little bit of computations and check why this is true. So why we can compute this Lyapunov exponent. So of course one reason is what else could it be, no? But this is not the best reason. So let's do it. So we have this SLNZ acting on the torus Tn in the obvious manner. So gamma and x, we map it to gamma times x. Now, this is induced, on the other hand, from the corresponding action, which is actually coming from a representation of SLN R on Rn, which again you take, now let's still call it gamma x, and you map it into gamma times x. Okay. Now let's discuss, before I go and make the computation, let me go and discuss a little bit this invariant measure. I said that there are some other measures that project not into lambda but into something different. So let's discuss this guy. So we have here G mod gamma, which is SLN R mod SLN Z. We have the diagonal group acting here. And there are some very specific orbits, some very special orbits, which are compact orbits of this A action on this SLN R. So now how will this build one of these compact orbits? So let's do it. So take a matrix gamma naught, any, so far I will put some conditions soon, but so far any, in SLN Z. Okay, now I will make one assumption. So assumption is that Rn splits as E1 plus En some spaces, eigenspaces for gamma naught. And I want two things about these eigenspaces. So I'm already saying a lot when I'm saying there are n of them. So it means that I have all eigenvalues real, particular, but could be the identity matrix. So assume the characteristic polynomial of gamma naught irreducible and so this automatically will tell me that all the eigenvalues are different, because if you have repeated eigenvalues, then the characteristic polynomial is reducible. That's a nice exercise if you never did it. Beautiful exercise, actually. And the last assumption I will make is assume that all eigenvalues positive. So real and positive. That's it. And why I care about all of this? Because once I have all this, I have two theorems. One is Dirichlet, which with this information and some work you can prove it, but he have done it before us, certainly. So unit theorem actually it's a special case under these assumptions, says that the centralizer of gamma naught so this is isomorphic to z to the n minus 1 semi-direct some finite group. And actually this finite group is essentially plus minus identities matrix. So sometimes you have it, sometimes you don't have it. So there is not much more than this. Yes, that's all it is. So we will forget about this f in a second. Okay. So this actually is important for later use, not yet. Let's go back to this splitting and this matrix gamma naught. So the main thing we care is that gamma naught, since we have this splitting, will be some matrix Q naught times some, how should I write it down? Let me write it like d sub t. Well, d sub t naught is e to the t1 naught e to the tn naught, which are the real eigenvalues. Okay, so the matrix Q naught is just taking this splitting and making it to the standard splitting of some order, whichever order. Okay, so far so good. Now, here is all I needed. Maybe I have a little bit more, which is important. So I have now any matrix gamma in this centralizer of gamma naught having positive eigenvalues, which, as I said, essentially all of them taking out this plus minus identity. So in this case, actually, it's not even a semi-direct product, it's a direct product because it's only plus minus identity. But anyway, I will have that gamma will be Q d sub t gamma. This gamma is e to the t1 gamma e to the tn gamma with the very same matrix Q naught. Okay, and this is because once I have this splitting into one dimensionals, the other matrices will have to respect this splitting. And once it has to respect this splitting, it means that they diagonalize simultaneously. Okay, so now what all this is telling us, let's call this guy gamma naught just to keep the notation. So this is telling us that when I multiply Q naught inverse by dt gamma, what I get is Q naught inverse times gamma. Okay, that's for every gamma. That's the first thing that it tells us, which means that dt gamma Q naught inverse times gamma is equals to Q naught inverse times gamma. So these guys are fixed point for this transformation on G mod gamma. So that's one property. The second property we can get, which again follows essentially easily from this Dirichlet unit theorem, is that if I take all these T1 gamma, T gamma is SLNZ.
How do you switch from the centralizer of gamma 0 to
Here.
That's for just the centralizers.
Yes, that's for every gamma in the centralizer of gamma.
But one prime is something stronger.
No. I'm just multiplying by gamma from both sides. So if I have equality,
I see.
then I have equality here. Okay. And then the whole game is that I can erase this guy.
Okay.
So actually, this property implies that this happens for some gamma, and that's how actually I should have started maybe from there. Yeah, maybe I discuss it later, which is a similar approach, but starting instead of constructive is deductive. But yeah, both are important way of doing the analysis. So okay, I take all these vectors in Rn such that the sum of t I gamma equals to 0, and gamma in the centralizable gamma, positive entries, positive eigenvalues. So I take all these guys, and this is actually a subgroup of the diagonal group, naturally, and it's indeed a lattice. This requires a proof that we will discuss in a second, but it's a lattice in this T1, Tn in Rn such that sum of Ti is 0. Okay, so I have this copy of Rn minus 1 embedded in Rn, which I identify with the diagonal group, which is a vector space. And I have this subgroup, and this subgroup is a lattice, but as I said, this requires a proof that it is a lattice. It will not be hard, but we will see it soon, that it is a lattice. Okay, once this is a lattice, I get exactly what I wanted. So I take D times Q naught inverse. So I apply the D group to this guy times gamma. So this is the D orbit of Q naught inverse times gamma, and I claim that it is compact on G mod gamma. And for this, I need to do the standard things, which is this Q orbit on G mod gamma is homeomorphic and isomorphic and naturally equivalent to D quotient by the stabilizer of this point. Okay. Now, what is the stabilizer? This is all the diagonal elements, D sub t, such that D sub t Q naught inverse times gamma equals to this. Now, this is a subgroup of D. This is all the D sub t. And now is where it comes this 1 prime, because 1 prime is telling me when I can solve this equation. And actually I get even 1, which is better than 1 prime, for that matter, which tells me when I can solve this equation. And the answer, if you look at 1 here, I have 1 second, which is Q naught inverse gamma Q naught equals to dt gamma. Now I transform this into, this is exactly the same as Q naught inverse gamma Q naught intersected with D. And then you can check that if d sub t belongs here, then d sub t q naught inverse equals to q naught inverse times gamma for some gamma, which implies it belongs here because d is in d, and I conjugate and I get it in gamma, and vice versa. If the guy belongs here, then it has this form, which implies it belongs here. Now, why is this equality so important? Because gamma is discrete. Okay? So gamma is discrete. I conjugate gamma by q naught, is still discrete. I intersect it with d, it is discrete in d. So I have that this guy is a discrete subgroup of d. Now, why is it a lattice? Well, I need it to be discrete, and I need to have co-compact quotient or finite volume quotient. But these are n. So in order that are n minus 1. So in order that this be a lattice, I just need to make sure that this discrete subgroup has maximal rank. And this maximal rank is given to me by Dirichlet unit theorem, telling me that I have Zn minus 1 rank on this group. Okay? So that's it. This is a lattice. The lattice is essentially stabilizer, because it's this guy, which is the stabilizer, and then this orbit is d modulo the lattice, so it is a torus of dimension n minus 1. And these are the compact orbits for diagonal action. Actually, this also can be read directly from here. If you go back from the proof, you take a compact orbit, then a compact orbit will have, as any other orbit, this form. The fact that it's compact is telling us that this is a lattice. The fact that this is a lattice is telling us that I have some, so it's the orbit of this q naught inverse, so that the q naught inverse do this game, and you have maximal rank. It means that you take any such gamma coming from here, so you take any element in this lattice, call it T naught, pick the gamma naught correspondingly, which will belong to SL and Z, and then comes the statement, and the statement is you have a full splitting like this. So all the eigenvalues will have to be different. The characteristic polynomial is irreducible, and blah, blah, blah. And this is essentially an exercise. It's not really very hard, because it has to do with computing the centralizer of this gamma naught you are picking there. And that is not so good. Okay. So that's how you bring the the compact orbits. And here is a very important guy, which started all the game, which is this q naught inverse guy. So it's the guy diagonalizing the gamma matrix. Okay. Now, this diagonalization is what push this Rn into these EIs. So if I take R sub I, the coordinate, height coordinate in Rn, and now I push it. Let's see how I wrote the formula. So if I push it by Q naught, this guy, this will be the EI. because if I apply EI here, this is the same as applying Q naught times Ri, and then diagonal maps Ri into Ri, and then EI maps. So why is this so important? Because this allows me to relate how the Lyapunov exponents and how the splitting is in the standard Rn versus what happens over the Q naught. So when we go back here, remember I told you this EI depends on the G, and in this particular case of EI of this Q naught inverse, what we are actually getting is that this is Q naught of Ri. And now comes a better thing. I can tell you that this is true always. So EI of any G, I will define it as being G inverse. Oops. Of Ri, essentially. That's what it is. Okay? But for this, I will need to be a little bit careful, and we are going to be careful in a second. And then things will become very natural and really very nice and safe. So let's do this last thing I did in a very global fashion. We, in a sense, already did it when we were playing with A and B and suspension of A and B. Now we do it again. So we have G times Tn modulo the relation. And here the relation is Gx with G gamma inverse x. Okay, now I will define a second quotient space, different quotient space. Actually, it will be modulo Rn modulo some equivalence prime. So what's the equivalence prime now is Gx will be related with Gx plus, now I have to be very careful, I think is Gn for every n in Gn, and actually, yes, I'm good with dimensions. So this is the first equivalence, and the second equivalence will be that Gx will be related with G gamma x. That's the second. So these are two different spaces. Okay, so both are quotients of G times Rn. If you want here, I could put Gr times Rn, and then it's this relation as well as Gx and n is in Cn. So this quotient brings me to the torus Tn here, and then the second brings me to the quotient space. Here is slightly different. If I perform this quotient, it will bring me into G mod gamma times Rn, and then the second quotient will bring me into this second space. And these are primes. Okay, the point is that these two spaces are the same space. Because I have a map H from G times Rn modulo the relation into G times Rn modulo the second relation, which is H of Gx is Gx. And I have to be careful because I may need to put here a G inverse. I may need to put it either here or here. I never remember. I think I have to put it here, actually. Who is clearly invertible, and the invertible is without putting the inverse there. Now, I need to check that this H is well defined. Okay? So this H, I define it from G times Rn to G times Rn. I need to make sure it maps the correct guy, and since I put the primes, I really think that it should be this. Let's check, okay? So when I do H of G x plus n, I get Gx plus Gn, and this is related prime with Gx, because that's how this prime relation works, and certainly this is equals to H of Gx, and Gx is related with Gx plus n. So clearly, related guys goes to related guy for this x plus n relation. Now for the other guy, I do H of G gamma, gamma inverse x, and let's see if I did things correctly. This is by definition G gamma times gamma inverse x, which is G gamma x, G gamma gx, sorry. And this is related with Gx, related prime, and this is H of Gx. And once again, we get that this guy is related to this guy, and they map two guys which are related. So the relations go to relation. Okay, actually this relation comes from a group action. So the group action 1 and the group action with the prime, and I'm intertwining both group actions. Anyway, so everything is very natural. So I have these two guys. I have G acting here, which is A Gx is A Gx, which from the dynamical point of view has the problem that I only actually see the dynamics happening when I cross fundamental domains. If not, I don't see dynamics happen, and then that's why it's hard to do computations and everything. And then I have the H map from here to here, so I can define the dynamics here by conjugation. Okay, I take an element here, I bring it back, I apply my G action, I go back here by H. And if I do that, let's just do it here. I take Gx, I map by H inverse into G inverse X, which I map into G inverse X, and then this is mapping into AG AX. So that's the action here. A star GX prime is AG AX. Now, what is the advantage? That I see infinitesimal, no matter how small the A is, I already see some distortion happening in the fiber direction. Okay, now it's not so hard what's happening when I look at the diagonal group acting in this G times Rn modulo the prime. Because in the second coordinate, it's just multiplying the diagonal matrix by x in Rn. And this takes the first element the canonical basis, multiplied by e to the t1, second element e to the t2, third element e to the t3, and so on. It's the diagonal action. Okay? Now I want to emphasize that it's the same thing I did here. It's exactly the same thing I did here. It's this change of coordinate, this conjugating maps. So the same thing as in here. So this H map doing the game. And why the Lyapunov exponents is what they are? Because that's what they are here. So it's e to the t1, e to the t2, e to the t3, e to the t4, e to the tn. Take logs, you get the ti's. Now, from the picture point of view, it's a very important picture. So here you have G times Rn modulo the first relation. So you have your G mod gamma in the base, which will have cusps and is not compact, whatever it is. And then over each of these points, you have a torus Tn. Very beautiful and round, because this torus Tn is Rn mod Zn. Okay? So, and then the dynamics only happens when you go around the fundamental domains or around the homotopy, and then you start seeing what's going on. Now, in the second picture, you still have this base, G mod gamma, with the cusp and everything. And now, over this point here, you will have one torus, which will be Rn mod G times Zn. And then here, so this is over G gamma. And notice that gamma times Zn equals to Zn, because gamma is ln Z. So if I take another representative, I get the same torus. Now, if I'm here, then it means that this Rn mod GZn, so this is very distorted guy when I'm pushing on the cusp, which means that the guy here will be a very long and thin torus, or very distorted torus. Okay, say the matrix G actually is e to the t1, e to the tn, where the ti's are really huge. Then it means that when I do this times Zn, I get a lattice whose fundamental domain is a very, very thin rectangle and long here, which means that this torus is very thin and very long. Okay, so that's how the torus looks here. That's how the torus looks here. The dynamics are topologically conjugated by a beautiful diffeomorphism. Now, the spaces are not compact, so the geometries, so the H is not a uniformly Lipschitz map, even though you can declare it an isometry, and then it's an isometry, but then it depends on what the metric you are putting here and what's the metric you are putting here. And since these are not compact spaces, the geometry depends heavily on the metric you are putting. But from the smooth ergodic theory point of view, we don't care that much because we care as soon as the guy go and come back to a compact region. And when you come back to a compact region, the Riemannian metric will be essentially the same up to some fixed distortion, and then whatever expansion you had, you still have it. Now, if you go and point all the way to the cusp very fast, directly, like these guys is doing, they are just shooting all the way to infinity, then what's happening is, yes, your dynamics is hyperbolic, because when I multiply by this matrix, that's the effect. I take identity here in the base. I multiply this identity by this e to the t1, e to the tn. I take my torus over the identity, which is the standard torus. I apply this matrix, and this becomes hyperbolic. So I have a very exponential expansion on each coordinate or contraction. Now, who pays the price for this is the size or the shape of the torus, because I will have a very exponentially distorted torus over here. Now, why this doesn't affect this conjugancy here? Because when I do the same thing on this other side of the picture, I shoot on the torus, even though the guy is round here, because on this picture all the tori are round. I never pass any fundamental domain, actually. I shoot directly to the cusp. So if it were SL2R mod SL2Z, I'm doing this movement all the way up. I never jump to a different fundamental domain. So if I don't jump to any other fundamental domain, nothing is happening in this other coordinate. Okay, I'm not seeing anything. So the comparison is useful when you come back to compact sets. If you are not coming back to compact sets, there is nothing to discuss. And since we are talking about measures, we care about coming back to compact sets by Poincaré recurrence. So, but anyway.
So one thing I don't understand is H is a very nice map.
H is a beautiful infinity diffeomorphism, analytic.
Yes, it is analytic. So how is it like?
It's not Lipschitz. If you try to put whatever reasonable Lipschitz business, I'm multiplying by G, and G has infinite norm. Or not infinite norm, but norm very large. So G times X has very large norm on Rn. Forget about the quotients. Okay? So look just G times Rn, G times Rn. And this map. From G times Rn into G times Rn. Now, the first coordinate you have put the identity, so yeah, that's not a problem. But in the second coordinate, you are multiplying by G. So if this vector has size 1, this vector has G times 1. And norm of G could be whatever it says the first coordinate, 30 millions. So it's locally Lipschitz, of course, as any infinity map, but it's not globally Lipschitz. So you have really big distortion. Okay, so I made the same mistake as I make always, but anyway, I think it was an important discussion, and we did all the computations, but we ran out of time, so I still have to give example 2, and then go back to the theory. So, okay, that was long ago, sorry.
So if we started with a co-compact lattice,
Then it's much nicer. Then, yeah, there will not be explosion, but you see what is the problem. But that's very important, actually. Let me try to do in these 2 minutes, since we are going to do example 2 on Monday. Let's try to see what happened here. Okay, let's say we still take G equals to S ln R, but now we take gamma a co-compact lattice. So then this G times Tn modulo relation will be a compact space. And so life is nice, but before I do this, I need to say how gamma is acting on Tn. So first things, gamma naturally will not act on Tn. You still can have gamma acting on some Tn for another large n. So you send gamma inside SLNZ. And once you send gamma inside SLNZ, that can be done. That's Margulis super rigidity tells you that that essentially can be done, or Margulis arithmeticity. And so you make gamma act on Tn. Of course, first things n typically would be much larger than n. Not so bad after all. We still have the picture and to work with. Then we face the second problem, which is I do G gamma, but now this guy has a number. It's not just a matrix. It's rho gamma inverse x. So that's how the relation first happened. And if you want to do the same we did for the second relation, you would have to do Gx related to whom? Well, G, and then remember it was x plus, because, okay, I forgot. I should do the other, which is Gx related with Gx plus n, which is how the torus shape goes. But then I have to distort the lattice Zn here by something depending on G. And well, the natural thing to do would be to do rho of G times n. That would be if you just follow the same construction, you want it to work, that's what you have to do. But now rho, this rho here, has to actually correspond to some embedding of SLNR on SLNs of SLNR on SLNR extending this guy. Okay, you will need this extension as well. Well, Margulis say both, yes to both things. So yes to both if n, little n, is larger than 3. Okay, so Margulis says first, there exists the rho from gamma is SLNZ, and second, actually this rho comes from an extension like that. So it's an essential because you have to take finite in the subgroup, blah, 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 but that's yes. And once you have this, then you're happy. This is a perfectly nice homeomorphism, uniformly Lipschitz, infinity diffeo, conjugated, the action here, the action there, and you can do all the business as you want. And all the analysis we are making as well. So there is no problem on all these discussions if you do that. And and again, but the point is having the uniform Lipschitz constant and all the compactness is not really much help. So you don't need it. We can go over there and not having the Lipschitz constant or anything, life will still be nice. You will need, yes, something which, when you try to apply Oseledets theorems and all this blah, blah, blah type of business, and the theory, you will need something like this. Now, this, the way I wrote it, is not very well defined even, because what is the norm of G on G mod gamma? There is not a well-defined norm of G for G mod gamma, but what is well-defined is you take sigma, the fundamental domain, for G mod gamma, And this will be very useful, because this has to do with the L1 integrability of the derivative cocycle, looking from here, looking from there, and blah, blah, blah.
So here it's sufficient if it's log L1 instead of
Yeah,
L1k.
but that's exactly the log L1, is this.
Yes, but for the general Oseledets, you said L1k, no?
Yeah, well, yes, that's only will give you a log L1, you're right, so you actually probably want a little bit more, but you will have more than this, so that's okay. So this is to do the very weak Oseledets. If you want to do the good Oseledet, you need L1k, not just, which will be L1 n minus 1. And, and yeah, this amounts to writing it differently and have it. Yeah, you're right. Okay, so Monday I do the example 2. I promise, or I try to promise that to not waste my time on Monday. Thank you.